Drunken Mathematics. Mathematics brought to you by somebody who's been drinking.
Okay, so imagine for a moment that you had the audacity to say, for any Pythagorean triple, if you just simply tell me the value of x and the distance between z and y, I can fill out the rest of the equation, and not only fill out the rest of the equation, but fill out an infinite set of primitive Pythagorean triples for each one of those things.
I don't believe you.
Pythagorean triples are three whole numbers that satisfy the equation a squared plus b squared equals c squared.
A Pythagorean triple, you take a right triangle, right? That's right. And then you make that x, and you make that y. And then that side's going to be z. That's hypotenuse. Whenever you square this guy and you square that guy, that's going to be equal to the square of that guy. So like you could even put like a square like that, where that length is x and that length is x. And you could put a square like this, where that's y and that's y. And you can put it like a square like this, and that's z and that's z. And if you were to add the area of this to the area of that, you get the area of this.
Three whole numbers that satisfied that equation would certainly be 3, 4, and 5, meaning 9 plus 16 certainly equals 25. That's by far the most famous Pythagorean triple. It's the one that a lot of different people use.
But you could have like other combinations, right? It wouldn't necessarily have to be 3, 4, 5. You could also have like 8, 12, and 15. I'll pretend like that's one. That could be one. I don't know. Okay. So you could have like 8, 12, 15, and that would be a one. Now, what's really weird? This is the important part. If you really want to know how many primitive Pythagorean triples there are, you could easily just write it like this.
Number, and then another number times another number, and you square it, plus that same number times a different number and square it. And if that equals that same number times a whole other fucking number, and you square that shit, unless that number we're talking about is 1, this shit ain't gonna fly as far as being a primitive Pythagorean triple. In other words, to go back here for a moment, 3, 4, 5, that all works. The coefficient is 1. 6, 8, and 10 don't work because the coefficient is 2.
See that? Isn't that cool? Okay, so like there's a friggin' infinite number of them. So that was easy. That was a quick video. But there's this other cool thing. Not about just Pythagorean triples, but this primitive. Oh fuck. Primitive Pythagorean triples throw out that whole coefficient shit. The coefficient shit is not that. It's just the coefficient has to be 1.
Extra little bit just for my little own satisfactory thing. Y has to be greater than X. That's all I'm saying. Because trying to say that 3, 4, 5 is a primitive Pythagorean triple, and then trying to say that another primitive Pythagorean triple is 4, 3, 5,
then you're stupid.
However, I'm going to add this extra little fucking bit. I'm going to be talking about the distance between Z and Y.
Delta. Delta in this case. And Z is always going to be bigger than Y, period, because Z is the hypotenuse, and the hypotenuse is always bigger than, any of the other two legs individually, but smaller than the other two legs combined. Okay. So, we can create a list utilizing an XY chart and a cute little formula. Let me write out that cute little formula for you. So let's say that the distance between z and y is going to be 1. All right? So we can write this cool little formula here and say that y, that's going to equal x squared minus 1 and all that divided by 2. All right? Interesting little thing. Makes a parabola. Kind of cool. Okay, so now if we make an XY chart, and we can just start throwing in numbers in order to figure out our y. Now, what I like to do to start off with is I like to double delta. And so that would be 1 times 2 is 1. Where's 2? Alright, so that's 2. And then let's just figure out what the fuck y is. Because this is what y is. So x, since that's 2, that's 4 minus 1. 4 minus 1 is 3. And we're going to divide 3 by 2. Oh, that's not a fun number. That's not a whole number. Well, that's not going to work. So we can just ignore 2, right? Because that doesn't come out. That's like a whole number and shit. Okay. So we just add another 1 to x, right? And we're gonna make that a 3. Okay. So now we're just gonna do it again. 3 squared is 9. We're gonna subtract 1, divide that by 2, that'd be 4. And remember what delta is. Delta is the distance between z and y. So you just add 1 to y, and you get z. Okay, cool. Works for that one. Not very cool. Okay, so it's not every number. So I'm just gonna skip the next one. I'm gonna go to the next one. Just for fun. We're gonna go to a 5. It's a 5. Trust me, it's a 5. Okay. So we're gonna do 5. That's 25. Minus 1 is 24. And that'd be 12. And then we add 1. And 5, 12, 13 certainly is 1 too. So if you do like 25 plus 144, 25 plus 144 is 169. And 169 is 13 squared. Okay, so that one works pretty good. We can do another one. Let's see. Let's go. What's that? Okay, so you're gonna do 49, and you're gonna do minus 1. So 49 minus 1 is 48, and divide 48 by 2, and that's 24. And then you make that 25. We can keep going with this. It's kind of fun. Seems to be every odd number. Let's go up to 9. 81 minus 1, that's 80. Divide that by 2, that's 40. 9, 40, 41. That's certainly one. I can keep going. We can do 11. So that's 121 minus 1, which is 120. 120 divided by 2 is 60. 61. You do another one? One more, just for fun. 13. 13 squared is 169 again. 169 minus 1 is 168. 168 divided by 2 is 84. And there you go. It's a nice little list of Pythagorean triples, and it of course always works because there's a very, very simple repeating pattern that happens with the x's, and you can certainly very easily see that when you take a odd number and you square it, it's always going to come up with an odd number. And when you subtract 1 from that, that's always going to become an even number again. You divide that by 2, that's always going to come up with something that's like a whole number. And you can see right here that it'll always produce primitive Pythagorean triples because delta is 1. Meaning that the distance between z and y is always 1. So the coefficient is always going to be 1. Okay, so that seemed pretty simple. There's an infinite number. Are there more than that? Well, I don't know. Let's find out. It's changed slightly. So delta is now 2. And we're going to be subtracting 4 and dividing by 4. That's kind of weird. Okay, so we're just going to double delta again because that was fun. All right, so that's where we're going to start. So, all right, 4 squared. What's 4 squared? 16. 16 minus 4 is 12, right? And then 12 divided by 4, that's a nice number. That's 3. And this time we're going to add 2. Well, that's 435. That number sucks. I'm not going to use that. But it was there. Okay.
When you change delta to 3, the greatest common divisor isn't ever 1. In fact, it's always 3. You change it to 4, the greatest common divisor is always 2. You change it to 5 and 6 and 7. The shit just don't fucking work. All of a sudden, it begins working again at 8. So, when the distance between z and y happens to be 8, all of a sudden this motherfucking shit works again. And it happens to be that the frequency of x, or the range of x, or the dicole of x happens to be 8, and that's just I'd call it a coincidence, but that's not really the right word. The rate of change of x happens to be equal to delta, but in any event, from 20 on, you just keep adding this shit, and you keep getting shit that equals shit that happens to make Pythagorean triples. So the greatest common divisor is consistently 1, and we can just continue this shit on as we please. Going all the way up to a delta 25, z and y being 25 numbers apart, we continuously develop all of these Pythagorean triples. Obviously not this one, because all that shit's divisible by 25, all that shit's divisible by 25, but none of this shit is divisible by anything other than 1, i.e. the coefficient of the original equation is in fact 1, so it is a primitive Pythagorean triple. So let's get to some really cool shit. So, notice in this shit, I just changed the frequency of x, or the rate of x, or the booby of x, to just simply 1. That means that x increases by the number 1 and nothing else. So that first one, 3100, happens to produce a primitive Pythagorean triple. And as you scroll down, if you're really paying attention to the decimals, you'll notice a pattern occurring. Eventually, we'll arrive at 3 whole numbers. However, they all happen to be even, so we're not too excited about that. As we scroll down, eventually we arrive at 3200. 3200 squared plus 3471 squared does actually happen to equal 4721 squared. And the greatest common divisor between 3200, 3471, and 4721 is 1. Okay, so I cleaned some stuff off and I changed some shit so that I can better explain this shit. Alright, so you see how delta is 1, and then it's 2, and then it stops working for a little while, and then suddenly it works, and then it works again, and then you gotta like double it, and then it's 25. So like this is a really freaking odd little pattern here. So I made this little this other column called root of delta. Now the root of delta helped me kind of figure out what all of this stuff is actually based on. So when you look at it over here, I divided this stuff up by I divided all the deltas up by what the root was. So it's either it's a prime number or it's an even number. So 1 is, in this case, we're calling 1 prime. I know it's not normally 1, but it's 1 now. 2 is, of course, even. It's also prime, but in this equation, it's being used as an even. 4 is obviously even. 3 is prime. So what happens is that the
order, or the times when delta actually works, is not just one simple equation inside here filling out all of these numbers to come up with this pattern. It's actually two different series of numbers squished into one. So it's every prime number and every single even number. Not only does it create a primitive Pythagorean triple, but it also creates a continuum of primitive Pythagorean triples. And you can see that here in looking at it over here. So here's our good old 3, 4, 5, and then here's our 8, 15, 17 being derived from a root even number, which is just 2 squared. It's not that it's every even number. It's not that 2 is even, and it's not that 4 is delta. It's this part of the equation right here that really kind of makes it all work. So what it is if it's an even number, then you square it and then you take half of the square. So it's not that 4 is a delta, it's that 4 squared, which is 16, and half of 16 equals 8. So 8 is the delta. We can go like a bigger number here just to have it make more sense. It's not that 12 is a delta, it's that 12 squared divided by 2 equals 72, and 72 is the delta. With prime numbers, all you got to do is square it. Forget the whole dividing that shit by 2. It's just, you just square it. So if this is a square of if this is a perfect square of a prime number, then it's going to work. There's an infinite number of prime numbers. There's an infinite number of even numbers. So there's actually 2 sets of continuums being created, continuums of infinity being created. So for every prime, there's for every single individual prime, there is an infinite continuum. For every single even number, there is an infinite continuum. So you can kind of see that, and I filled out a whole lot going all the way down here so that you can really kind of get an idea. I was actually having some fun with this. Every so often when I'm bored, I go in there and I find like another one. But all of these work out perfectly. All of these numbers in bold over here. So when x equals 21,252 and the distance between z and y is 8,712, then z comes out to 30,277. And this really does keep going on for a while. I forget exactly how far down I went with it, but I had a lot of fun. Oh, there we go. That's about the end. Now, of course, what's cool is before I even find the first x, I can find the next next delta that'll work, because it's just evens and primes. So as long as I have those will of course keep working. And then over there on that evens and primes tab over here, I've got all of the evens and primes all listed out, which they're not actually all hand typed in. I just actually got a list of prime numbers and a list of even numbers, and then sorted them. Thank you, Excel. So that's the magic of it. So this little percentage, the guess of x is off by. So I was trying to figure out, when does x begin to work? When is it happening, and is there any relationship to pi in there, or to delta in there? What's neat is the relationship is actually a little bit closer to 1 plus the square root of 2. That's what that means up there. 1 plus 2 raised to the 1/2 is the same thing as saying 1 plus the square root of 2. So here I'll change the rate back down to 1. And what this guy actually does, here, I was doing a little bit of testing earlier. So I will copy that formula right back into here. And you'll see here, if you take delta
and you add 1 plus, or you multiply that times 1 plus the square root of 2, you get 118.29, blah, blah, blah. So I just rounded it. I rounded it down. That got me to 118, which obviously doesn't work. But then the next number is 119, and that one does work. And 119 squared plus 120 squared does equal 169 squared, or 13 to the fourth, if you wanted to look at it like that. And then as you scroll down here, then you see a reoccurring pattern, and then all of a sudden, bam, there you go. Here's another one that works. And you can keep going. There's another one that works. You'll see that the frequency of the ones that work start to increase and then suddenly decrease, but the overall, there's a 49. So if I were to take that number, the delta 49, this is what I was playing with earlier. If you take every 14th number, you start to generate this cool little list right over here. That's not really every. There we go. You start to generate this little, this cool list over here of 1149, 111111, 49. And so after a little while, I sit here and I play with the numbers until I figure out what the exact equation is for it. And what that exact equation is, so it's like, say for delta 9, it's not really every 6th number, sometimes it's every 12th number. So the equation for figuring out the frequency, the real frequency of x, is taking -1 raised to n plus 1 is really what that means up there. Then multiplying that times S4, which is this is my first coefficient here, so 3. For 9, you multiply that times 3, and then add my next coefficient, which is 6, and then you just add that to n minus 1, the value of n minus 1, which is 33, and you come up with 39. And then you'll notice that this comes up with a very perfect little list of all those numbers working out, and we can even sit here and expand that, I believe. If I'm lucky and I do it right. Yeah, I did it right this time. So you'll see that that comes out with a nice little formula. And you'll see over here, just to demonstrate that it does not work if you just simply put in 6, I'll come over here and I'll put in 9 for delta. I'll leave the rate of change at 1, and then I'm just going to move this guy to 33 because we already determined that that was the first one. Okay, so we see that 33, of course, works right off the bat. And going all the way down here to 51, that's the next one that works. Let's quickly do the math. 6 numbers? Oh, no, it wasn't 6 numbers. I'll do later. Oh, yeah, it was 6. Yeah, it was 6 numbers. It wasn't 51, it was 39. Well, anyways. So if we just do it, if we only did it by 39, or if we only did it by 6, you'd see that you would get 9 every third number. So what this equation over here actually takes care of is that. So here's some good stuff to remember. Y equals x squared minus delta squared over 2 delta. Delta equals z minus y. When you have a prime number, you square it. When you have an even number, you take half of whatever the square of it is. And you start x right about delta times 1 plus the square root of 2. Of course, if you want to, you can just double delta and start x there, and that's kind of the same thing. Now, some of you might be wondering how this relates to Fermat's last equation. So x to the nth plus y to the nth equals z to the nth. Well, to make this formula work, you've got to do some funky stuff. So you take y, and you raise that to the n over 2, and that equals z to the nth minus delta squared over 2 delta. Now, delta also has to change. Unfortunately, it's no longer the distance between z and y, it's now the distance between z raised to the n over 2 and y raised to the n over 2. Now, once you realize that you're dividing n by 2, it starts to make a lot more sense that when n is a even number, you have these semi-nice conical shapes that they get a little bit squarer as n increases. But then you have this radical shift whenever n is an odd number. Everything looks bizarre. You get this weird little wave thing that starts to happen. And that, I really think it makes a lot more sense now, knowing that you're actually having to divide n by 2 in order to get all of these numbers in.